Okay, so welcome everyone. Today we have Professor Serkant Adıgüzel with us, and in our Summer Institute context, lectures don't go incrementally. Yeah, like no lecture follows the previous lecture. There's just like random bunch of lectures depending on who's free on which day and at which day. This ideally, to me, should have been the first lecture of the Summer Institute because it shows us some of the most recent advances in statistical methods, especially statistical methods that are very popular and high in demand, not just in computational social science, but also standard social sciences as well. Today you're going to do regression discontinuity?
No, not. I mean, since we wanted to do some application, I removed RDD part. So compared to my previous lecture, so it's all gonna be PID only.
Okay. So this is definitive. His previous 2023 lecture is already online.
Yes.
And actually, it is the most watched video of Summer Institute's YouTube.
How many times? Do you know?
I don't remember, but it's like by far it's very
like 200 at most.
No, because Summer Institute lectures are restricted only for people
okay.
college.
I see.
It's
Makes
not
sense.
public. Because we don't want to give random people too much power.
Then there will be comment section.
Exactly. To me, this actually would be ideal as the beginning lecture of the Summer Institute. And I'm very delighted to have Serkant Adıgüzel with us. He is an assistant professor of political science here at Sabancı University. He has a PhD in political science from Duke University in 2022. He has a master's in economics and a BA in economics and political sciences, all from Causal University. He's a faculty fellow at the Association for Analytical Learning about Islam and Muslim Societies, also part of the Machine Learning for Peace project of the Dev Lab at UPenn. He served as a faculty affiliate at Harvard Kennedy School's Middle East Initiative for the academic year of 2023-2024. Before joining here, he was a research fellow at Harvard Kennedy School's Middle East Initiative. So with that, all of that led to this moment. So Serkant, just thank you so much for joining us.
Okay, well, thank you. Well, welcome. First of all, I see some familiar faces, but majority of you are not from Sabancı. So I was talking previously. So this is a bit tricky because I checked your profile, so it's quite heterogeneous, which means this was very tricky to prepare. So I'm sorry that it's going to be repetition for some of you. So it's going to be too straightforward for some of you, but that's I think that's probably the case for every lecture on this camp. So. Okay, so it's going to be the ID. Yes, previously there was also RDD, but given time constraints, I think removing RDD was was the sacrifice I had to do. But if you have any ideas, any research design where you're like thinking about incorporating RDD, we can talk about it later. Okay. So why the ID? I want to bring this paper first, which came out recently by Guy Grossman and co-authors. The title is The Credibility Revolution in Political Science. And political scientists are necessary. I mean, in the poster, so someone wrote computer science under my name. So I'm a political scientist, not computer scientist. Yes, which is fine. I mean, it's for political scientists, I suppose. So it's fine. So so this is credibility revolution in political science, but this applies to all social sciences. There is also an econ version of this. I'm sure there is someone is writing the sociology version of this, where they look at more than 90,000 articles between 2003 to 2023. Check the paper. So 174 political science journals. So, any journal you can think of is probably here. And what are the results? I mean, as you can guess, so credibility, when I say credibility, it's causal inference, right? So to make causal claims in a credible manner. And if you look at the trends, so okay, so there are a lot of things. So first one, for instance, here, the design-based studies are increasing in the last 2 decades. And the old way of doing things, like model-based studies, right? Adjusting your model statistical regression model by adding covariates, right? That's something, I mean, still obviously popular, but the trends are declining. So it's like mostly design-based studies are picking up. And if you look at what are these design-based studies, and some of them are obviously experimental, and survey experiments are, it's also increasing. But also, if you look at non-experimental, DID is one of the most popular methods there. Also, regression discontinuity. Well, if you look at the y-axis, it's still around 8% of quant papers in political science, maybe 6, was employing one way or another DID. But if you also look at top 20 journals, these methods are employed more. Okay, so if you wanna, if you're aiming publishing in top journals, and this says something, right? So design-based studies are becoming more popular, and DID is one of them. So that's why I'm introducing it here today. Okay, so let's start. And obviously, so you cannot do experiments all the time, right? That's the gold standard to establish causal stories, right? To tell a causal story. But most of the time, you cannot randomize stuff, right? Or nature doesn't do the randomization for you, right? So you need to work with observational data. What does that mean? You observe things, right? Data generating process is something you don't create, you just observe it. And in that realm, right, panel data is something we use a lot. Okay, so I mean, before switching to the idea, I'll briefly mention what is fixed effects. Obviously, this might be too straightforward again for some of you. Then we'll talk about the idea, and then a version of the idea where there is staggered timing. Okay. Again, as I told you, I mean, most of the time we work with observational data, and the idea is one way that can allow us, right, to tell a causal story with observational data. That's why it's a design-based solution, right, to the causal to tell a causal story. So you handle that problem, right? You handle that. So given that we have this problem, meaning we need to establish that causal story, the idea is one of the many designs that can allow us to tell a causal story. Okay, I mean, this is the most famous example. You probably, I mean, if you ever got some econometrics class, you saw this paper, right? Card and Krueger 1994, where they actually look at fast food restaurants in Pennsylvania and New Jersey. So they asked, okay, so New Jersey in 1994, I believe, they raised minimum wage, okay? And then, well, if you ever take an econ class aside, whether minimum wage is increasing or decreasing employment is a huge debate, right? And, one can look at, restaurants, fast food restaurants in New Jersey, and then conclude that, hey, look, New Jersey restaurants are employing fewer people than Pennsylvania restaurants. So minimum wage destroy jobs. Well, what's wrong with this, right? First, I mean, that difference can be because of a lot of reasons other than the minimum wage increase, right? So, and these are what we call confounders, right? So we are interested in the relationship between minimum wage and employment. But obviously, there are a lot of things that can explain both, and they are called confounders. So, and why the name confounders? Because they confound the relationship between X and Y, right? We are interested in the effect of X on Y, but a lot of things can confound that relationship. So what we really need in this case is a counterfactual New Jersey where minimum wage didn't happen. Well, that counterfactual New Jersey doesn't exist. That's the fundamental problem. And in fact, that's called the fundamental problem of causal inference, right? What is the fundamental problem? We simply don't have counterfactual New Jersey, right? Well, what are we going to do? Are we just going to stop? No. Well, we can use the data, right? Observe data to estimate that counterfactual New Jersey, like in this plot, right? So we simply don't have it, but we can estimate counterfactual New Jersey by simply looking at, for instance, Pennsylvania restaurants, right? That's what they do in the paper. And how to do this? Well, nice thing with panel data is that you can actually observe same units over time, okay? So that gives you actually some leverage, okay? So first you can compare units to themselves, right? So you can compare one restaurant in 3 months. So you're essentially comparing restaurant to itself, which is actually a nice way of comparing things because it controls for everything that is constant, right? So because if you compare myself with myself in 2 years, right? And I'm trying to explain something that changed in my life, well, probably IQ is not driving that, assuming that IQ is fixed. I don't know, maybe it's changing if there are biologists, I don't know, right? So things that are constant won't explain that outcome. So that's the nice thing with comparing units to itself. Another thing you can do, well, you can also compare treated units change. So in this case, for instance, New Jersey restaurants with Pennsylvania restaurants change. So now we have 2 changes, right? So I'm comparing New Jersey restaurants before and after minimum wage increase, but I'm also comparing Pennsylvania restaurants before and after. And that after is again after New Jersey implemented the minimum wage increase. So the second one is what we call differences in differences because there are 2 differences there, right? One is you compare units to themselves, right? And then you compare that change with a control unit's change. So there are 2 changes. So since the first one is fixed effects, let's briefly talk about what fixed effect does. So in a fixed, I mean, this is like if especially economists, they like fixed effects regression, right? I also have a meme. Do I have it here? Okay. See, that they like fixed effects in every regression. So why do they like it? Well, first, I mean, unit fixed effects. Well, again, as I told you, you compare units within themselves. So assume like a regression with country fixed effects. Well, that's great. You're comparing countries within themselves, right? You're comparing Turkey with Turkey. So things that are unique to Turkey, that also things that do not vary in time, right? Time invariant stuff, you control that by design with country fixed effects, right? Because after all, think about the type of confounders we can have here, right? Confounders, again, what do they do? They actually confound the relationship between X and Y. So let me actually, so we are trying to explain the effect of X on Y, and then you have all these sorts of confounders that affect both X and Y. So you need to somehow account for these things, right? And you can have time variant confounders, meaning those things that vary in time and also time invariant. So the nice thing with unit fixed effects regression, for instance, right? You can actually shut out, right? You can actually shut down one type of confounders, which are time invariant ones, right? Because if you compare unit to themselves, things that do not vary in time are absorbed. So like country's culture. So you're trying to explain some, I don't know, phenomena, and culture cannot confound that relationship anymore, right? If you use country fixed effects in that regression. Assuming culture is also fixed, maybe it's not. Well, it's not definitely, but it's slow moving, right? So it's a slow moving thing. So, or location, definitely not changing. So, right, I think the continents are also moving. So anyway, but it's moving slowly. And how to do this practically? I mean, you probably all know this, right? But I, want to bring that up anyway. So especially in R, you can use FEOLS function from SICSS. This does run very fast. Okay, so if you want to do fixed effects regression or even just regular regression, use fixed very fast. I mean, try and you'll see the difference because Underwood, I think they use C, I suppose. So I'm looking at our computer scientists in class here. So that's why it's fast. There is also PLM, but I don't use that much. But also it's one of, I mean, these two libraries are popular. Again, fixed effects, they absorb anything constant about a unit. And that's the nice thing. You don't now have to worry about these confounders anymore. I mean, remember, like if we did this in a traditional one, where you add covariates into your statistical model, right, to control. Someone might say, hey, what about X, right? What about this? Have you ever controlled for this? And if you ever submitted to a journal, and I know some of you already published stuff, you probably got these reviews, right? Say, hey, what about that? What about this? That's a never-ending process, especially if you have some reviewers that are, very, anyway. So by design, that's why you can actually solve this. Like at least one part of the confounders, you don't have to worry about it anymore. But what fixed effects do not absorb are the things that change over time, right? Anything that is changing over time, they are still there. They can still confound the relationship between X and Y. Well, what else can you do? Add a time fixed effect, right? That's a common upgrade that people do, which is called two-way fixed effects, right? And time fixed effects, then it's going to absorb anything that happened to everyone at the same time, like COVID, right? That's the classic example that we can use. And this is actually two-way fixed effects is an estimation strategy, but I'm going to show you that actually in a simple 2x2, this is going to be one way actually to estimate the ID, because the ID is a design, and one way to do this is via two-way fixed effects, okay? In a simple 2x2, and yes, fixed, and you can add more fixed effects, right? And that's gonna actually, and that's obviously that's why do people do this? Well, because it handles a lot of confounders. You don't have to worry about those confounders anymore. This is from there is this guy, Minnesota PhD, who's quite popular on Twitter. Vietnamese guy. Anyway, you can find it. It's from him. I had to give him credit. Okay, for instance, like just a silly example. Does economic growth in 1 year predict higher liberal democracy scores in next year? Okay, so let's use VDAM data here, for instance. I don't know if you ever use VDAM. VDAM is one of the major data sets where you can learn a lot about countries, institutions, democracies, corruption, you name it. It's an expert coded data. I don't know, maybe you served as an expert at some point. I never did it. So they do surveys. They send surveys to experts, and then they create these indices. So we can use, for instance, liberal democracy index that they create. And then the predictor is GDP per capita growth. Let's run through the three different regressions and just talk about what they, each coefficient actually captures, okay? Well, I also have some code here in case you want to try it out, but the slides I already shared it, so you can also do this later whenever you want. So nice thing with VDAM, they already have the library in R. You can just download into your environment directly. It's just not on CRAN, it's not on central repository, so you need to install the library with the dev tools, so from GitHub. And then I'm using again fixed test. That's the library I use. First, just some cleaning. I filter the data, then I create my legged version of economic growth variable. Then I just run a simple pooled regression. Why pooled? Here there is no fixed effects, okay? It's just a pooled OLS, okay? And that's the estimate, 0.44. So what does that mean? Well, it means if you increase X by 1 unit, Y is going to be associated, right? So Y is going to increase by 0.45, which is a lot because liberal democracy index is from 0 to 1. So that's a large effect, right? And it's also statistically significant, right? Look at the p-value. What is the p-value? That's the probability, right? That's the probability of observing something as extreme as the one we just observed under the null hypothesis. What is null? Here, that growth has no effect, okay? So what's the problem here? It compares all countries, right? All country years to all others. Meaning you compare Sweden, Germany, right? With, I don't know, with Turkey, right? And it's not really apples to apple comparison here, right? There are a lot of things that are different between these two countries, right? So economic growth, democracy index, well, there are a lot of things that are different between Turkey and Sweden, for instance, right? You know, historical trajectories, institutions, culture again, right? And you know, there's a lot of literature about democratization, right? And determinants of democratization, and you know, they are all here. You know, anything you can think of is all here. So that's why this coefficient picks up a lot of things that are not in the model. So it's biased. The coefficient is biased. So, well, I mean, we can upgrade this. So we can have country and country year fixed effects. So how to do this in R? So again, practically, you have, this is how to do it in R using FEOLS. And the first one is country fixed effects because I only have country variable there, right? And then the second one is two-way fixed effects, country and year. And if you look at if you compare now the coefficients, they change drastically. Well, not surprisingly, right? So when we compare countries to themselves, because that's what country fixed effect regression does. You compare Turkey with Turkey, you compare Sweden with Sweden. GDP growth last year is, you know, the effect is close to zero, right? If you just look at the second model, right? And then if you also add year fixed effects, then I mean, the effect is still modest, but it's not statistically significant because the standard errors are also similar, right? It's less than 1. T-stat is less than 1. So it looks like that the growth democracy story here is mostly driven by cross-country differences, which, you know, there are a lot of different things between countries. And within country changes is not actually driving this, okay? So why did I bring this up? Because difference in differences is actually designed where you can use two-way fixed effect regression to estimate the ID effect, okay? All right, let's start with this. Well, can you see what this is? Is there anyone from London? Yes. So you know the story, right? So this is a fountain. Let's write it's a fountain where people get water, and this is actually, I mean, this is the story is there is this first original DID is coming from London. There is this guy John Snow. He's yes, he's into epidemiology, but apparently I also check his bio. He's also an urologist. And he actually implemented drug on Queen Victoria back in the days. Anyway, so he believed back in the days that cholera is waterborne, not airborne, because that is these people believe it's just smell that is causing cholera. Okay, but he thought otherwise. He thought that it's because of contaminated water, and he started collecting data. So, and back in the days, you know, there were two companies pumping water from River Thames, okay? And in 1894, there were two companies, they were both pumping water downstream, okay? Which means the water was already polluted by the time it's downstream, right? And actually in 1852, only one company, so that's Lambeth, they actually moved their pump upstream, which means it's cleaner water because it's not going through London, right? The upstream. So, and cholera struck again in 1854 once Lambeth actually moved its pump to upstream. And this is actually a simplest the idea you can think of where there is before and after, there is control, and there is also treated. what is treatment here? So it's clean water, right? So Lambeth, by moving its pump upstream, now they are pumping clean water. The nice thing is that apparently back in the days, I mean, people didn't know from which they are really getting water. Okay, so these people were really comparable, and it was just like you're getting from one, not another, is just like coincidence, right? So look at so these are deaths per 10,000, and look at the changes. So before 1852, they were very similar, but after there is a massive reduction only in households where they get water from Lambeth company. And see, we have now what? We have two differences, before and after. Right? If you just look at Lambeth, for instance, from 1852 after 1852, there is a reduction. But how do we know that this is because of clean water? Maybe now there is also cleaner air, right, in London. So, well, that's why we have a control group here, right? Control group, if you look at the control group, well, they are also exposed to the same air, just like Lambeth company, right? So, and the DID estimate is just the difference between these two differences, okay? So, and this is like the famous example where this is the first known example of a DID in history. So that's why I wanted to start with this. And the difference is like that estimate minus 123 is our DID estimate. Okay. And DID by design, you'll see soon, is going to handle two sorts of confounders: time invariant. Why? Because you're comparing units to themselves, but also time variant. Why? Because there is also a control group, right? So the control group, the whole purpose of having a control group is to infer what would be the time trend, right? How would these time variant confounders work in the absence of treatment? So we infer the role of time variant confounders by simply looking at the control group. Okay. Any questions so far? So yeah, the slides are, by the way, on I mean that that's already probably available. So I mean you can have it. You can also take photos, but it's going to. I mean it's already available, I suppose. Yes, sir.
I have a question for the example that you have given in the beginning. So the pool had a small coefficient. It was 0.24.
Yes.
But it's kind of a dynamic panel model. In logarithmic scale, you have the growth on the left-hand side and you have the left GDP on the right-hand side. So
yes.
Percentage change.
Oh, yes. So, yes, it's in log terms. You're right.
And the other thing is when you compare it to the two-way fixed effects, the coefficient is declining drastically.
Yes.
And I'm not sure if from one year to the other, since it's dynamic, this effect should be that small.
That's small. So you mean the third model?
There is a path dependence.
Yes.
Yeah.
So I mean, yes. So I clustered standard errors by but and yes, these are very simple examples. And yes, so these are, since it's on the x and so on the right hand side we have log. So on right hand side it's just the index. So it's level log. Yes. So that's level log regression. And regarding the I mean, yes, I don't handle any sort of serial correlation between observations. So they are not IID, right? 1 year observation is probably not independent of the next year's observation. The only thing I do is a clustering by country. But again, yes, these are just very simple, toy examples. Yes.
That's Johnson example.
Yes.
As an example of spatial difference.
Nice.
So we are using the same
Yes.
stuff.
That's nice. And also epidemiologists they probably also use it. So it serves for a lot of purposes. Yeah.
I also have seen this example, the paper from Friedman,
Uh-huh.
the importance of qualitative reasoning.
Really?
Researchers should have some innovation
Uh-huh.
and by observing the field
Yes.
in person.
So yes, it serves a lot of. I mean, it's an excellent design. Anyway, there is also another story where he starts collecting data there, and so there was this one clustering, and maybe that's also you use in special econometrics. So there was a pump, and then there are a lot of cases around, and he thought that specific Broad Street pump is problematic. Then there was brewery just next to it where no one died because they were drinking beer.
That water is clean, by the way, where they drink beer.
Yes,
they
because
get sick.
they were using and there was also a lady but she died, but she was living very far away. Apparently, she liked the taste of that water and getting it delivered to her home. So yeah, yes. So okay, going back to the Card and Krueger, this is so April 1992, New Jersey increasing minimum wage, and Pennsylvania didn't. So what they do, the authors actually look at fast food restaurants. Why fast food? Because I mean that's very standard, right? What you get from McDonald's, it's pretty standard. It's so standard that there's also this Big Mac index, right, where you can actually economists, they are using it to estimate living costs across countries because the product is so standard. And the question is obviously, did the wage hike destroy jobs? So they have panel data here. So they observe restaurants. So they actually call them, they do surveys. They collect data from different restaurants before and after. So we have two time periods here. And this data is part of the QSS. So QSS, so Kosurima, so now he's at Harvard. He has this excellent textbook, Quantitative Social Science, I suppose, the name, yes, it should be. So there is a corresponding R library that I use for teaching purposes. So the data is already there, cleaned. So I'm going to use that data. So since, I just use data mean wage, and it comes from this QSS library, okay? So what can we do? I mean, I'm just creating full-time proportion of workers. That's the outcome I'm going to be looking at. So full-time workers, the share. Okay, so I'm creating before and after. So two different variables here. So this is how the data looks like. So we have 67 restaurants in Pennsylvania and 291 from New Jersey. Okay, that's how the data looks like. So what can we do? Given this data, we can do three things. One is cross-sectional comparison. Okay, maybe let's also have this 2 by 2 here. So we have New Jersey, we have Pennsylvania, and then we have before and after. So given this 2 by 2, we can do different sorts of comparisons, right? So one is just cross-sectional comparison, meaning that we can actually compare. So let's do A, B, C, D maybe. So we can do B minus D, right? So B minus D would be the first comparison we can do. That would be cross-section, right? Why cross-section? Because I'm not using the time component here, right? And when I do that, again, I have the code here, so you can play with this at home if you want. So it looks like 4.8 is the difference. So cross-sectional differences is 4.8%. Well, it looks like that the full-time employment is slightly higher, around 5% higher in New Jersey than in Pennsylvania. Well, is this because of minimum wage? Well, again, a lot of confounders exist between restaurants in New Jersey and Pennsylvania. First is state law is different, right? I mean, their state economies are different. So, a lot of things actually can explain this difference. So it's very hard, right, to attribute this difference to nothing else but to minimum wage. So that's why it's not very a good comparison, because maybe New Jersey, the full-time employment was already higher in New Jersey in the first place, right? That could be also the reason. So if you look at, for instance, this was also around 4.8. Then nothing is changing, relative, right? If you look, I mean, nothing is changing in terms of baseline differences. Well, the second thing we can do is just compare before and after. And as I told you, this is a nicer comparison in the sense that it's a, you're comparing units to themselves. It's unit fixed effects are there, right? So each unit is, compared to its own baseline. So you can actually do B minus A, right? That's before and after. Before, after. So if you do this, it's actually 2.3. See, it's now smaller. But again, it's positive. So there seems to be some effect, which is positive. So minimum wage increasing full-time employment. But then again, comparing units with themselves, yes, it handles time invariant confounders, right? Things that do not vary in time, that are unique to New Jersey. Let's say culture again, right? New Jersey culture, whatever that is, or whatever that means, that's handled by design here, right? But again, we still have time variant confounders right here. So before and after, because that could be things that also vary in time, just like minimum wage increase. Maybe there was an economic boom, right? Things were going great for New Jersey and they decided to increase minimum wage, right? Maybe this is just about that economic boom, right? I don't know. Maybe there was an oil discovery and things were going great, and maybe this is picking up the effect of that oil boom, right? So that's why, yes, we handle one type of confounders, but the other time variant ones are not handled here. So you see where this is going, right? Well, what if we compare these, we combine these two sorts of comparison? So yes, so this is the problem. Again, anything happening between is also picked up here. But, so that's why this cannot be because of minimum wage increase only. So, so that's why we can, we can actually leverage, right? So we can actually use both to kill both kinds of bias at once, okay? So because cross-section, it actually controls for time shocks because you're comparing just one time, right? One at a time. Before, after, it actually controls for state level difference, but not for time shocks, right? Or time variant confounders. So in order to kill both at once, the ID is actually useful. Okay, what do? So I do essentially two kinds of difference, right? So this is B minus A, and now we have D minus C, just like the Jon Snow example. So B minus A minus D minus C, right? So this is what the ID estimate is, okay? So two differences at once. And that's what I calculate here. So the ID is actually greater. So the ID here, let's just also write, well, I also have it on slides. So it's 6.1, okay? The ID is actually quite larger than others. So now let's think about it. So the ID is larger, okay? So for instance, think about before and after. It was actually 2.3, okay? The ID being larger means what? So it looks like that things were not going great for Pennsylvania restaurants in terms of full-time employment, okay? Why? Because just before and after for New Jersey is if it is 2.3, the trend for Pennsylvania was negative, right? There was a falling employment trend in Pennsylvania, okay, for whatever reason, right? Maybe there was an economic recession overall. So that's what Pennsylvania serves here as a control. So we infer the role of time variant confounders by simply looking at Pennsylvania, and it looks like, right, there was a declining trend in Pennsylvania. So we picked that up from Pennsylvania. So this same, by the way, here I didn't use any regression at all, right? It's just simple differences. Just calculate the averages and then take the difference. The same DID estimate I have here could have been actually estimated with a regression as well, two-way fixed effect regression, right? So since we have 2 by 2 here, the simple regression would actually pick up the beta 3 that you see there is going to be our DID estimate. Okay, so we have treat, right, which is 1 for New Jersey, 0 otherwise. post, a dummy variable for post, which is 1 after, 0 before, and then their interaction, okay? And well, first I need to reshape the data because the original data, if you load it, you would see it's in wide format. So I need to make it long to estimate the regression. And this is how I estimate it. And look, see, this is exactly what I calculated manually, right? 6.1. And my thing here is I don't print it here, but I also have the standard errors. So I can also do the hypothesis testing here. All right. So 6.1 is the estimate here, just like I also have it here. Well, it's not statistically significant, but there seems to be, right? It's positive, but I mean, at least we can conclude is what from this is, minimum wage at least is not destroying jobs, right? Minimum wage increase. And why beta 3 is the ID estimate? Well, if you just plug the numbers in it, right, you would see beta 3 is actually picking this up, okay? So just, just plug, for instance, plug 0 and for treat and post, that means what? If treat is 0, which means it's not treated, and post is 0, that means before. So that's actually Pennsylvania before. So this cell. Well, if you plug that number, you would see that only alpha is there. So intercept actually is Pennsylvania before, right? That's the average full-time employment in Pennsylvania before the minimum wage increase. So you just plug the numbers, you will see that, and you would see that the ID. So this difference is actually picked up by beta 3. Okay. Yes.
Use the intercept for the time variant and the slope. So not kind of like the steepness or the acceleration.
So, but this is by construction. So I didn't use anything. So I'm simply plugging the numbers. So whenever I see treat, if I just put 0, and then whenever I see post, if I just put 0, see, so that is going to be canceled. Okay, my laser is not working, but treat, so that's gonna 0, that's gonna cancel out. That is going to be canceled out. This is going to be canceled out. The only parameter is going to be alpha, right? And think about substantively what alpha represents. So when treatment is 0, that means it's not New Jersey. When post is 0, that means it needs to be before. Well, among these 4 cells, we are then now here. So which shows that alpha, when we estimate the regression here, the intercept, so this is actually, and do this at home, because you have the data, calculate the average share of employment in Pennsylvania before the minimum wage increase, and you would see that it's this number, okay?
So the intercept when you have 2 static time points. So you have like a point in time, static point in time.
Yes.
And a static point in time, and you you have like a before or after.
Yes.
But you can also do it on a more dynamical.
No, just 2. It's 2 by 2. Very simple. That's why alpha picks up this cell. Okay. So yes, it's mechanic. I mean, just by algebra. All right. So that's why beta 3 is going to be the ID estimate. And now, I mean, things are going to be more complicated in a second. But first, again, let's stick with the ID. So we now infer counterfactual New Jersey by looking at Pennsylvania time trend. So we say, hey, things were not going great for Pennsylvania restaurants. They were declining. So then we say, okay, if there was no wage increase in New Jersey would have looked like just like Pennsylvania, right? And that is the counterfactual New Jersey we create by looking at Pennsylvania. And the difference between actual New Jersey and counterfactual New Jersey, this is the ID estimate, okay? Well, you can now obviously ask, well, how do you know that Pennsylvania is a good control here, right? So maybe it's not a good control. Well, we'll talk about that in a second, not in a second, but well, no, in a second actually. So there is one single assumption that we need to make here, and that's called identifying assumption. So what is that? Maybe you heard that phrase, right? What's your identification assumption? That is the assumption we need to make to tell a causal story. Otherwise, no one is going to believe that, indeed that's causal, right? So the assumption is actually is coming from there. So in the absence of treatment, we assume that New Jersey would have followed the same trend, just like Pennsylvania. Well, what's the problem here? We just make an assumption about a counterfactual, which doesn't exist. And I always, counterfactuals do not exist. And I teach this for undergrads, and then I made this movie suggestion, Coherence. Have you watched that? Coherence, low budget movie, but excellent movie. So you'll see there were counterfactuals. It's about parallel universes. Very low budget, but excellent movie. Watch it, Coherence. There, for instance, I mean, I don't want to, but there are, parallel universes where you can actually have, a counterfactual version of you. While obviously in real world, that doesn't exist. We simply use the data, Pennsylvania data, to estimate it. Well, so that's why the assumption is the New Jersey restaurant, so New Jersey would have followed the same trend. Well, obviously, this cannot be tested directly. How would you know? Counterfactual doesn't exist. Well, there is a second best thing we can do is, if you have data, just look at how these two states trends were evolving before the treatment, right? Well, in this case, we don't have the data. We cannot do it, right? We only have 2 by 2. So for a DID, you would actually need, right? If you want to publish it in a good journal, you would need multiple time periods before treatment starts to show that these trends were kind of parallel, right? So it's something like this. I mean, this is obviously simulated data because the real data is just 2 time periods. It's not 2 by 2, but you would want to show something like, obviously this is too ideal, right? And this is just visual. You can also test this more formally. It's called event study plots. So you can do actually, what you can do is event study, meaning that you can actually estimate the effects for different time periods, and you would want to see null results before treatment, right? If they are comparable, right? I mean, there should be null results, but then after treatment, you would want to, you would want to see the effect, right? Effect of that treatment. So if there is some sort of differences in pre-treatment, that signals that maybe control group is not a proper control, right? Is not a good control. So, and obviously this is hypothetical, but you would want to see something like this where things are more or less parallel. And this actually, because that, what we do is, okay, well, if New Jersey didn't increase the minimum wage, we just extrapolate from here, right? By looking at Pennsylvania, we say, hey, New Jersey counterfactual will be somewhere here, right? That's what the control group serves. Well, things were too easy until now. It was just 2 by 2. The real life is not like this, unfortunately, right? So it's most of the time, policies do not go out at once. So, for instance, Turkey's healthcare reform, where there was this family physicians, right? In 2010. That was first implemented in Bolu as a pilot province in 2009, I suppose. Then gradually it was extended, this family physicians. And then there's one paper actually published in Journal of Public Economics, Resul Hoca and others. So they look at the effect of family physicians on things such as mortality. To what extent family physicians affect this? And also, I think not just mortality, maybe also baby, something about baby's health as well. I don't know, check the paper. But the thing is that treatment is happening over time, right? It's not happening all at once. So, and most of the things, these policies, they actually are not rolled out at once, which means we no longer have 2 by 2. We have many treated units and treated at different times. And to make our lives more difficult, and I told you that we can estimate 2-way fixed effects, right? To uncover the DIE estimate. Well, if you do this with a staggered timing, with staggered design, you're gonna be wrong. Okay, so you cannot use 2-way fixed effects anymore. All right, and this is post 2020 literature. I mean, I have the references here. So what these guys, guys, at least these are, I think, all guys. So what they show, these papers show is especially this Goodman Bacon's paper, two-way fixed effect coefficient that we have here. By the way, this is just the generalized version of this simple 2 by 2. So see the same regression here. I can generalize this to multiple units and multiple time periods with unit and time fixed effects. Okay, it's just the same thing, just generalized to see. I have factor unit, factor year. That means what? I have year fixed effects and unit fixed effects. Let's say country. Then a dummy variable for treatment. So this, the coefficient for treatment is actually what this paper shows is just a weighted average of all possible 2 by 2s. Okay, so when you have multiple time periods and multiple units, two-way fixed effect actually is just a weighted average of many 2 by 2s, such 2 by 2s. Okay, and the problem is that some of these 2 by 2s include controls that shouldn't be controls. All right, so those are forbidden controls. So those are actually early treated units that serve as control units for later comers, later treated units. And that's a wrong comparison. When you think about it, right? If you want to estimate the effect of a policy on Y and you are comparing treated units, well, that's what we shouldn't do, right? And this is, I mean, this came pretty late. So the one paper that we're going to replicate, published in 2017 in American Economic Journal, which is the AJ, it's a, a good journal. And well, back in the days, this was not kind of known. Okay, so that's why, for instance, we would see that results actually change when we use a different solution, different estimator. And why does this happen? I mean, I have a simple example here. Think about 3 groups. Okay, never treated group, early treated, and late treated group. So we have 3 groups here. So you can have 4 different 2 by 2 here, right? So you cannot compare K, which is earlier treated, with U, never treated, L with never treated. You can also do K versus L over the time when L was not treated. And then you can also do L versus K, but this time K is already treated. The 4th one is the problematic one among all these 3. Okay, let me actually show you in a figure. So this is, we have 3 cores, and 4 different comparisons. And if you compare L versus K between these time periods, right? So they are here, I mean, yes, let me see. So from TK to T, yes, so from TK to so here, right? So here the problem is when K is already treated. So that means it's oh, I already have it. So it's already problematic comparison. So think about like comparison 3 that I mentioned between K and L, where L is controlled, which is fine. L is not treated until this point in time. It can serve as a control unit, but and K is already treated, so it's just treated versus control. But look at comparison 4, where L is let me see. So L is not treated yet, but K is serving control here. But the problem is K is already treated because it gets treated starting from TK. And this is forbidden comparison. And in that literature, econometric literature, this is called a negative weighting problem. So meaning, there are all these forbidden comparisons in the data. All right. So solution is what? I mean, you see the problem. What is the solution? Just use clean controls. Do not use cohorts where, do not use cohorts that as controls when they are treated. It's actually a simple solution, right? But you cannot use two-way fixed effects because mechanically it's using all sorts of possible 2 by 2s, and it's just a weighted average of all these 2 by 2s. So then we need to use some other estimators. Yes.
Okay. So I understood that. Can you talk about that?
Yes.
So
Is there any way, like, so we know that after TK, it starts like it starts retreated. Is there any way to remove the effect of the treatment using the other group and update the case so that we can kind of
Remove. So removing.
So basically, untreating this.
That's actually okay. So that's what we are actually kind of doing, right? When we say like we are estimating counterfactual, you're actually right. What you're doing essentially is right. It's in separate. It's just the same actually. So what's the solution? You can use other estimators. There is this excellent source, Ashraf Naqvi. I think he's an economist, where he keeps track of all these new estimators. And the idea of, I mean, economists are probably, they know it. So, if you look at this literature, it's very dynamic. It's, a new paper comes out every single week at some point. Right. And look, these are all 2021, 2024. So these are all different estimators, but they all solve this negative weighting problem. So they all use clean controls, all right? And, check how they differ. There is a practical guide, which is a very nice, in an accessible format, because these are not, as you can imagine, right, not very accessible unless you're well versed in econometrics. But this is, a nice guide. There was also recent LLM that I think Callaway and Sant'Anna, they release it. You can find it on LinkedIn, or I can send you the link. Fine-tuned LLM, I suppose, for the ID. So you can chat with that. So to just see which one is more proper given the research question you have. So now I'm gonna walk through Callaway and Sant'Anna, a 2021 method. So what they do is, so they actually define these cohort-specific ATTs. So the idea that we estimate is actually it's called the average treatment effect on treated. Okay, so those are ATTs. What they do is, so the building block for Callaway and Sant'Anna is these cohort time specific effects. Yes.
So if you compare the treated that was earlier treated with the treated later, aren't you then getting, I'm not really understanding yet what was the building, because aren't you just getting more information about the sustainability of the treatment, and whether like a longer time period compared to a shorter time period of treatment?
So
difference in treatment efficiency.
Yes. So if the task is to estimate the effect of treatment, right?
Yeah.
So it's like either you're getting it or not in this case. It's not those. So if you're interested in those, yes, that might be, but that's not we are after it. So it's like a binary treatment where once it's turned on, you cannot switch off. So you can think of all these more complicated designs. What if there is treatment, right? It's turned on and it's turned off after a while. That makes things more complicated than this is once you get treated, you're treated, just like family physicians. Once, yes, it's like, think about it like a policy, right? But yes, there are all these designs. So there is actually a recent paper again by Callaway's, I think, and Callaway Sant'Anna, where they look at what happens when there is treatment, but it's continuous. I think it recently came out. So yes, so anyway, so going back to Callaway Sant'Anna, so they define these cohort time effects where they essentially, create these by simply looking at, by simply using controls that are never treated. In their notation, that infinity sign means they are never treated. Okay, and that, I mean, given that they are not treated, right? So so this represents what? So this represents the average effect for cohort that is treated at time G. Okay, and obviously parallel trend assumption is still here. So, and no anticipation, meaning that they don't anticipate the treatment. Cohorts are not anticipating it. You can actually uncover the ATT for that cohort by simply looking at, again, it's just the same actually when you think about it, all right? It's just that we now have a proper control group where they are not treated yet. Okay, it's see, these are just the averages. Okay, this is just an average. This is just an average, and that's that's the ATT for that cohort. But the problem is now we have a lot of ATTs. If you have multiple cohorts, you have multiple ATTs, right? Well, you can just combine them, right? So you can actually have a single ATT, which we'll do by the way, you know, you can simply combine where, I mean, obviously it's weighted mean, where weights are equal to, the, you know, they are proportional to their sizes, okay? And nice thing here is that it's very transparent about which units are, which units serve as controls. One problem with two-way fixed effect is that's under the hood, you don't see it. Here, it's transparent. You can actually specify whether you want to use never treated groups as control or not yet treated groups as control. Now, because think about it, right? We can actually use early treated groups or sorry, late treated groups as controls in certain comparisons. L can serve controls up until time TL, right? So you can actually use not yet units, not yet treated units as controls as well. Going back to Turkey's example, every province became part of the reform at some point, which means we don't have a never treated group at all. So we have to use not yet treated group as controls. Okay. Well, I'm gonna stop here because, well, and the nice thing is that, so I mean, we can combine these in different ways. And I mean, you're gonna do it in the application. I have this, I mean, this is a stupid, not stupid, but this is a simple example from their help. You know, they have, I mean, obviously they have this documentation where they show how to use this. I just copied and pasted from there, so I'm not gonna go over this because we're gonna do something better. But this is how we estimate it. So we estimate ATT, GT. So this is again, it's employment. This example, youth employment, and then again the minimum wage increase. But this time, this is by counties. Okay, so we have a county panel data set here in this example, which means you're gonna have different, because not every county adopts this minimum wage increase at the same time. So you're gonna have different ATTs depending on cohorts. So here cohorts are defined based on when they get treated. Okay, so which means you're gonna have different ATTs for each cohort. Then you can actually aggregate them by group, by cohort, by year, calendar, or just a single ATT, just like our regression estimate, right? A single ATT. So I mean, I'm just skipping this because we're gonna do something very similar in you know, as exercise, but the slides are here, so you can always check it out. All right, just to, you know, wrap up. So I mean, in a single 2x2, right? We estimate this DID with a two-way fixed effects, right? But when things are not that simple, using two-way fixed effect actually is problematic because, you know, we're gonna be doing these forbidden comparisons. So that's why we need to use something else. Callaway and Sant'Anna is one, but there are also other estimators, which, by the way, again, they check this resource, which actually, so he's actually collecting all these different packages as they come, and also the different estimators. So it's just a repo of everything collected. Okay. Any question? Yes.
For the task, do you possibly have the data in a different format? I don't have a data license, so I can't open it.
So you don't need the data license. So if you're using R, are you using R?
Yeah.
Okay, so you don't need it. Just a library. Yes. Yes. I mean, I don't know economists, so they are still I mean, there's a path dependency. So they are still using Stata, which is not an open source, unfortunately. But we don't need Stata. That's the nice thing. We're gonna do it in R. Okay. So maybe let's give a break. Then we can do the No, we were talking about this paper. So if you want to check, I mean, if you want to read more about minimum wage and employment, I think this is a good paper. Doruk Cengiz and others, KJ. Okay, so now, I mean, so this is, I prepared a handout, but this is more like you guys doing stuff, and I'll slowly scroll down, and I think you have the data. Let's slowly, so we're gonna be replicating and then extending the paper. So I don't know whether you had a chance to look at the paper. So this is the economics of rights. Oops, sorry. Okay. Tamam, küçültüyorum tekrar. So the economics of rights, does the right to counsel increase crime? American Economic Journal, Econ Policy. So this is 2017 paper. So where they look at, so apparently there was this reform in Israel where they extended the right to publicly provided legal counsel to suspects in arrest proceedings. So before, this was not the case. And the thing for us is this was rolled out district by district over time. So this is a staggered timing. Okay. So, and in the original paper, if you had a chance to look at this, they actually employ two-way fixed effects, but we just talked that, this is actually not a proper way of handling things when there is staggered timing. So that's why we're going to extend this with Callaway and Sant'Anna's estimator as well. Okay. So first, well, we're going to need some libraries. Maybe start with that, open your RStudios and start coding again. So, I mean, I already have it. I don't know if you want to do it together or you just want to follow. I'm not going to code. So the code is already there. So read Stata 13 is the library to read Stata files. So if you don't have it installed, I think you already know, right? You're proficient enough. So just to install packages and then type the package you would need. There is also panel view, which is a very useful library to visualize panel data. Others, I think you probably have it. Maybe SICSS, you don't have it. Model summary, you might have it already. ggplot and deployer, I'm sure you have it if you used R before.
It works, everything works.
Okay. If you get stuck somewhere, we can. Any question about libraries? Okay.
Some libraries have other, like,
They call it.
dependencies. It tells you what that dependencies you install that package as well. So it's like iterative.
Yes, there might be some additional libraries needed. And again, if you need to work Stata files, you don't need Stata. So just use our free and open source. Don't use licensed stuff. No need. Universities, they do have license, they do provide sometimes licensing, right? But still, I think it's just a waste of money.
Yeah. Who uses it?
People still use SPSS. Universe. Well, time to change. Because it's free. It's free. Yeah, I agree. It's like maybe or like any, I think, script-based like programming language it has steep learning curve, but after like 3-4 months.
I think it's nice because we're going to work with older like this.
Yes.
And then you just
Yeah.
send them the syntax and they are
Yeah.
wizards.
Yeah, that's it. Yeah, SPSS, it's like, I think there is no script, right? It's menu-based, which, horrible for replication. But there are scripts in SPSS?
Yes.
Okay. All right. I didn't know it. See, I'm that biased. So. All right. If you already installed the necessary libraries and if you call them, now read DTA 13 is a function that's available to you, which then you can use to read the data. So the data is, it's a panel data, more than 2,400 observations. So these are districts per week. So the unit of analysis is district week, I suppose. Let me see. Yes, district week. Unit of observation is district week. Okay. So this is something you do, right? Once you install data, first you inspect what's going on inside. So dimensions. So dim is allowing you to check the dimensions of the data set. And if you just count districts, you can actually see the districts and the number of observations. So we have more than 4,000 weeks, sorry, 400 weeks. Okay, and these are the districts. Any questions so far? Am I going too fast or? Can you see it? You can see it, right? So that I can make it bigger if you want.
That's trouble with R.
And yeah, if you're new, maybe sit next to people who are more like feeling confident. That might be a nice way. Yes, maybe do it with your friends. I'm just going to pull up the original paper as well. All right. So did you confirm? So did you run this to check the number of districts? Okay. Yeah, there is a week counter from 0 to 415. So these are from 1996 to 2003. Okay. So there are, and this is just an artifact of working with Stata, then importing from Stata. There are leftover value labels, apparently West Bank, Mahash, and National. If you just look at the levels of district, so this is factor variable. So if you look at the levels, you would see there are different labels, but they don't exist. So this is, I mean, just a side note, which is fine. I mean, it doesn't change anything. So, for the replication and extension, we're gonna need 3 variables actually. 3 main. So one is whether there is public defender. So this is the main treatment, right? So what happened is if you, check the paper. So during arrest proceedings, states started providing legal counsel. So apparently they were not providing during arrest. So they were providing only after your charge. So now they implemented this reform where you are also having a counsel during arrest proceedings. Okay, whether when the judge decides you to arrest or let you go, but you're not charged yet. And this is implemented gradually. Okay, across different districts. So that's why public defender is 1 when you're offered that option and 0 otherwise. And 2 outcomes that the paper is interested in: share of court approved arrest, so whether the judge is arresting you or not. And second is the log median duration of arrest. Okay, so which obviously if you have a counsel, right? So obviously the counsel is gonna probably defend you better than you do. So, and the expectation is you're less likely to be arrested. And also if you're arrested, the median duration would be smaller, right? That's the expectation. And so duration is in log terms. Going back to Pelin Hocam's question, right? So if it is log, that's so when we estimate the coefficients, it's going to be in percentage changes. All right, so let's visualize the treatment rollout. So it's staggered, which means we can actually first visualize it. Look at the design. Okay, so panel view is an excellent library. So you can actually see which district is treated when in one plot. Okay, so how to do this? There is obviously a panel view function. It asks you certain things. First, so court approved arrest and public defender is the treatment. Court approved arrest is the outcome. Data, the indices, unit and time variables, unique. And the name of the variable so there is also no, sorry. So this is a type treat is the treatment outcome. So treatment status. So it's not the outcome. So because the same function allows you to also plot the outcome, but here I'm just going to plot the treatment status. So if you just do type treat, it's just going to tell you 0 or 1, whether that district is treated or not. And then some cosmetic labels for X and Y. See, this is what it produces. So I'm going to go back to the function again, but this is what it's going to produce. So in case you want to.
This plot is basically the plot that you show us slides before, right? It's the equivalent of it. So in time, when it was treated.
Yes, exactly. Yeah, it was just so it was just a line. Now it's see, these are weak counters. So for instance, Tel Aviv is treated when I don't know 150 something weak. So see, so there's a difference. This is this is what makes it more complicated, right? It's staggered rollout of the policy. So I'll wait here. Let me. So if you cannot produce it, let us know. Maybe. And this is a ggplot object. I think under the hood, it's just ggplot. Panel view is just calling ggplot in the end. And again, the function also allows you to plot outcomes as well. So instead of treatment status, we could also have plotted outcomes too. All right, so I'll continue slowly then. So, if you look at the treatment timing, see, beach district is the latest treated group. North is before that, south is, So, if we, now we're going to use two-way fixed effects. So, which I told you that it's going to give you a weighted average of different 2x2s, which means, for instance, Tel Aviv is one of the early treated districts, right? So when we use two-way fixed effects, so Tel Aviv is going to end up as control group for later, right? For later treated districts like North and Beach, despite being treated. So Tel Aviv is going to be a bad control, right? A forbidden control, which is going to be the issue in two-way fixed effects, right? So there is no never treated group here. Every district is treated at some point, which means when we use Callaway and Sant'Anna, if we specify a control group as never treated, the code is going to yell at us, yeah, because there is no never treated group. All right, now we're going to, if you come this way, all the way here, so now we're going to estimate the main results in the paper. So let's replicate it. It's table 2 in the paper. Let me first show you the paper. So this is the paper that we're going to replicate. So what's your conclusion? If you look at this table, what's your conclusion? So write the counsel. Does it have an effect on arrest? The first two columns are arrest, court approval of arrest. So likelihood of court approval happens. So what happens to court approval for arrest? Those coefficients are what? Negative, right? The first two. And this is 0 or 1, right? So that means what? 0 minus 0.05 is, it tells you what? Can anyone? So, well, it looks like that something is decreasing, right? The outcome is decreasing. So, and the outcome is whether the judge is gonna arrest you. So the probability of arresting you is decreasing when you have a counsel. That's what it says, right? And how much? That's 5.3%, right? So 5.3% decrease in likelihood of getting arrested when you have a counsel. And is this statistically significant? Well, we don't see stars here because that's they didn't start at something because of all these obsessions with p-values, p-hacking. So is this statistically significant? Well, you just divide the coefficient by the standard error, right? If it is around more than 2, that's we still do that right in our. So yes, it is statistically significant.
So the next slide, 5%, area
Yeah.
impactful.
So that's an excellent point. So we are always obsessed with statistical significance, but what about economic, right? Substantive size of the coefficient. Well, first we need to check what's the average, for instance. So given, right, what's the average share of people who are arrested in the first place? Well, if it is already low, then this might be big. But if it is if it is already high, then yes, it's it's not that high. So that too, but also let's assume maybe only 10% are arrested in the first place. Then 5 is relatively at least. So how are we gonna run that regression? Now we're gonna need to run 4 regressions. So here I'm gonna wait a little, but you can also copy and paste from the PDF if you want. So this is what we're gonna see. This is two-way fixed effects, right? We have districts and time fixed effects. See, I wish I have my laser, but what is that? Mouse, yes. So this is what? This is gamma. No, I'm sorry for my Greek alphabet knowledge. This is lambda. No. Lambda. I don't. I actually was quite proficient when I was doing my master's because macro classes they were using a lot of these letters.
Maybe it's epsilon.
I don't know. Whatever that letter is. So this is delta, right? Delta and what? Gamma? Tau. Okay, let's call it tau. So apologies if you know Greek, tell me. Well, so this is district fixed effects and this is time fixed effects, right? So this is again two-way fixed effects regression where beta is going to be our DID estimate. But again, this estimate is going to be biased, right? Well, because it's staggered and there are going to be forbidden comparisons that we are going to be doing here. So all 4 models that we see in the paper are here, okay? So see the outcome and then the treatment, then the fixed effects. And well, there are also time trends that the original paper is adding. So I also have them in model 2. So there is district specific linear time trends. How to do it in R? So district times beat counter, right? So district specific linear time. And then, well, that's it. I think that's the only thing they add. Model 3 and 4, that's a different outcome. So that's log median duration. And we cluster by month district because that's what the original paper does. So clustered by region month. So that's what we do here too. Okay. All right, let's run the regressions and let us know if you have troubles. Any trouble? I mean, you don't have to run all. Maybe just run one and then you can do the rest after if you want. It's fine. And well, unsurprisingly, we're gonna be replicating the original result. Yes. Well, what is it perfect ordinarity or?
It's removed all of the district variables.
Really? Maybe it's, maybe, okay, can I see?
Yeah.
So basically, every function.
So center, there's a node, so, oh, these are district dummies that are, I think it's fine, right?
It's like
These are, just do summary and one. Let's forget the result. I think these are just the district dummies that are dropped and it should be fine.
Well, I think it's because of the variable trap.
Yes.
Kind of a discrete variable.
Yeah.
Instead of using that, maybe we can use Boolean transformation, but it's not possible in case of this FEOLS. We
Uh-huh.
use cholera package for that.
So, yes, for the, if you wanna do it explicitly, yes, either do it manually, but here, yes, it's gonna do, so when you do weak here district, for instance, fixed effect there, it's gonna do it demeaning automatically under the loop. It's gonna do it, so, yes, so it's not, so I'm not adding, so you can actually run fixed effects, right, by adding dummies or doing transformation, demeaning, so it actually demeans it by weak here and district. So as long as you see, when you do summary and then it shows you the coefficient for public defender, I think you're gonna be replicating the paper. I mean, when I do it, oh yeah, so actually, let me see what oh yes, so I think the collinearity is the main effects that's gonna be fine. I mean, you're gonna be uncovered, I mean, the treatment effect is going to be estimated anyway, but you're gonna get the warning, because, well, it's gonna tell you if, so what is dropping is going to be, printed as a warning. So this is going to be the table you're gonna be, well, by the way, how to create this table? It's not in, oh, sorry. So it's here, model summary. So model summary is yet another great package if you want to use it. It produces publication ready tables. Okay. So that's what I use. But you can simply look at the summary. You don't have to create this exact table. Just look at the summary for all these regression results for regression models. And then you're gonna actually see the coefficients are actually identical, right? I mean, there is rounding, but it's just the same coefficients. So we successfully replicated the paper, right? But what's the problem, right? So, well, first, maybe let's talk about the results. So it looks like that based on first two models, right? The console actually decreases the probability of errors, right? And also a decrease in duration of RS. So this is in log terms, right? So that's why it's going to be around I think 16%. So I have it somewhere. Let me see. Oh yeah, here. So the treatment decreases the probability of RS by around 5% and the duration by around 15%. Okay. So since it's log term, should exponentiate it, and that's going to be around 15%. And these are robust to adding time trends as well, right? That's what the paper shows us. Any questions so far? Yes.
Familiar with random.
Uh-huh.
So how do they? So I'm assuming the fixed effects models are something.
Yep. So random effects, I think statisticians and econometricians, what they call random effects differ. So I think, so when you say yes, I think econometricians say they also sometimes use, instead of fixed effects, right? They actually use random effects as well. But yeah, I think it differs a lot. Hoca, I don't know, right? Because random effects model, what statisticians call random effects differ from. So I think what they refer is like some sort of a mix, right? Where I think model slopes as well. I'm not sure.
It is because of basic assumptions. In the random effects model, you're essentially assuming that you are taking the variables randomly, so that it's covariance with the error term should
Yes.
be zero. They should be orthogonal to each other.
Yeah.
But in the case of fixed effects, you allow for that.
So
But there are some shortcomings of fixed effects here.
in fixed effects, we actually allow different intercepts. One slope, but different intercepts. So that means what? For instance, counterfactual effects. What does that mean? You're gonna have different intercepts.
Yeah.
Because after all, it's a line, right? It's just a regression line.
Yeah.
So if
So your
intercept,
starting point.
yes, the slopes are going to be the same, but the starting point is going to differ in fixed effects models. For every country, right? The intercepts are going to differ. So essentially, you're having different lines for different countries, but the slopes are going to be the same. Because after all, we have just one slope. Yeah.
With random factors, and you can have like both.
Mm-hmm.
So
Both meaning.
like both so only intercepts,
Uh-huh.
also it needs slope difference, or both intercepts and both slope difference.
So that's the thing. So slope cannot differ in fixed effects. Yes. Yeah. So, but yes, I mean, depend. I think like if you ask statisticians, their definition of random effect models are going to be different than econometricians. There's some confusion, I think, in definitions too. Yeah. Yeah, it's about the error term. In like econometricians, right? It has to do with the error term. So whether there is a random, right, random slope within the error term, right, versus not. I think that's how they define it. But statisticians for statisticians, no, I think it's a totally different modeling strategy. But I don't know how they do it. Yeah. All right. So then once we have the models, then you can just use model summary. I think use model summary if you want to just have these publication ready tables. Okay. Well, so the results show that this is working, right? Treatment is working in the sense that duration is decreasing, right? The arrest duration decreases, and so the probability of getting arrested is decreasing. But as we talk this, right? There are now forbidden comparisons like Tel Aviv, right? It's an early treated group, which means it's going to be a control group, right? It's going to be a control group at some point for North, for instance. Remember, North is one of the later treated groups. If you look at the plot, right? Tel Aviv is going to end up as a control group while treated for like Beach or North, which is an issue. So that's why actually these results are biased. Okay, so the coefficients are biased because it actually includes forbidden controls. Okay, so what can we do? Well, let's just do Callaway and Sant'Anna. So to use Callaway, so there is a DID library. Okay, if you if you install all libraries, DID is part of it. So DID is the library to estimate ATT GTs that we mentioned. So these are cohort-specific ATTs. Okay, and you're gonna need, well, it needs to be in long format, the data always, right? We already have it. So there is also, you will need a group variable. So this is just how the package is designed. Okay, the function is gonna expect you to have a group variable that tells you when the unit is first treated. Okay, so and you're gonna need 0 for never treated groups. It's just by choice. I mean, that's how they write the package. All right. So you will need a variable that tells you when the district is first treated. So let's say if it is 124, that number has to be 124. And if it is 0, that means it's never treated. But we're not going to have zeros here, right? And then a numeric unit ID. It needs to be numeric. If it is character, then it's not going to run. Okay. So, all right. So then I'm just getting these first treatment because I need that right? I need that. So I need to know, it's already in the data, but I need that as a variable by itself. So I'm just extracting it and then joining it again. So, okay, so that I will have first treatment dates as a column, okay? Because I don't have it, so I need to have that. So I'm just extracting that information, which is summarized. See, I'm just grouping my district and then taking the big counter, the minimum of that is going to give me when these are first treated, okay? Which we already know in the panel view, but I'm just extracting it here programmatically. Then just joining it so that now I have that info. First treatment is part of the data now. So left join is just right. You keep the data and whatever comes is joined. So that means if there are missing stuff, it's going to have NAs in the left data, which is the main data set. And then we need numeric IDs, so I'm just constructing these numeric district IDs. Okay. Okay, so once we have all these three things, so the group name, that's the first treatment. So that's essentially a numeric column that tells you when each cohort is treated, right? Then we have a big counter. That's the from 1 to 400 something, right? That tells you that tells you the time, right? That's that's our T name. That's time variable. Then ID name. That's district IDs. These are numeric, right? Then obviously Y is just the outcome. G name is that's the group I told you. So you can also add covariates, but we don't have any covariates here. So it's just one. So that means just the intercept, right? There is nothing. And then control group has to be not yet treated. Why? Because we know. We don't have any never treated group. Okay, have you come this far? So did you ran all any issues along the way? Let's wait. We have time. They are done? Okay, great. Well, perfect. Okay, now we're gonna have ATTs for each cohort. Again, cohorts are defined based on when they are treated, which means I think all districts are treated differently. So actually, essentially, cohorts are districts here. Why? Because each district is treated at different times. So cohort is equal to district in this case. But if there were two districts treated at the same time, they would be one cohort, right? So cohorts are essentially districts just because they are treated in different times. So while there is also a warning that you might get here, some cohorts are small because we only have six districts here. Well, it's just how the data. It's just about data, right? There's nothing we can do about this here. All right. So first, now we're gonna have cohort specific ATTs. Well, how to present this, right? Well, one thing we can do is just a single ATT, just like two-way fixed effect regression, right? Just a single coefficient. How can you aggregate that? There is another function within this the ID library. It's AGGTE. So that's aggregate. So it's going to aggregate it, aggregate the ATTs for you. So you don't have to do it manually. You can obviously extract ATT GTs, right? Cohort specific ATTs. Then just take the average based on the size of the cohort. So here, but you don't have to do it manually. Obviously, if you just do type simple, that's gonna give you a simple coefficient, just one coefficient. Average. So that's going to be weighted average. Okay. And this is the result. So this is the coefficient estimate. This is the standard error, and this is the confidence interval. By the way, you might ask if you remember it was just again the average, right? It was just differences in averages, right? The ATT GTs. So what about the standard errors? Because it's not a regression. Standard errors here, it's bootstrapping, which means there is actually so what you do is you essentially add a noise, right? So you essentially do sampling with replacement, and then you get different results every time you do this. And you do this 1,000 times, let's say, which means you're going to have a sampling distribution, meaning you're going to have different results. And once you have the sampling distribution, you simply look at the 2.5th and 97.5th percentile, right? That's going to give you the confidence interval. So these are not analytical confidence intervals. You know, there's no like, you cannot derive this by formulas, by bootstrapping. Anyway, I mean, it's not important how we get it, but what we get is important. What's your conclusion? Look at the confidence interval. Does it include 0? So that means what?
No.
So it's not statistically significant, right? And it's 2.9. So this is, let's compare it with the original result. So it's almost half the size. And you know, it was already small, right? We talk about it, maybe small, maybe, I mean, it depends on the median, the average share. Maybe someone can check it, by the way. What's the average arrest rate? Maybe check it quickly. And but irrespective of that, it was around 5%, and this is now around 3%, right? And more importantly, the uncertainty around this estimate is higher than imagined, right? The regression, if you look at the standard error for the regression, it was tiny. That's why the result was significant, but here it's actually not, okay? One problem, obviously, not problem, it's just the nature of the data. We only have 6 districts here, right? So, and if you look at the data, so standard errors here are clustered by region month. So it's not by district, it's by region month. So it's actually, you know, the artifact of how you handle standard errors. So that's why it's a bit tiny in regressions compared to what we get here in the bootstrap regression. So, and yes, so I mean, we already so I have some writing here, so that explains what might be deriving these results. I mean, obviously, one is about what goes into the controls. So what we did here is purely clean controls, right? We didn't use Tel Aviv because, I mean, we didn't use like Tel Aviv after it is treated. I mean, by design here, right? But two-way fixed effect actually was using Tel Aviv after it is treated as a control in certain 2x2s. So that's actually, that was wrong. Once we fix that, it's almost half the size, the effect, and it's not statistically significant, okay? One thing we can do, remember the parallel trends assumption that we discussed, right? So how to test parallel trends assumption? I mean, you can visualize this, right? One way of visualizing this and doing this more formally is the event study. So what you would expect in an event study is, okay, so there is, by the way, this is relative, meaning relative to the treatment, okay? So here you're treated. If you're here, you're not treated. So what you would expect is if before treatment, there shouldn't be difference between treatment and control groups, right? That's the whole reason, right? I mean, unless, because if they differ pre-treatment era, then that means they are not that comparable, right? So that identification assumption is not plausible. But here we see it's all null, meaning the difference is, you know, so the 0 is part of the, right? 0 is within the range, 95%. And if you look at coefficient, it's very close to 0. So treatment and control groups are not different, which is reassuring, right? So, okay, so parallel trend assumption is plausible, we can say. But what about the effect of treatment? After the treatment, look at the effects. So this is like 1 week after, 2 weeks after, right? So it's like goes that way. So all the way to 10. And you know, it's around 0. Meaning the effect of treatment is, you know, is not, you know, there is no effect here. That's what it says, right? So, so something like this you could have done, right? So obviously first you need to do, again, I don't re-estimate, so I don't do estimation here. So I'm simply aggregating these cohort specific ATTs differently. So here I'm just aggregating by the length of exposure, okay? So by length of exposure, it means, you know, it's just essentially, you know, like 2 weeks after treatment, 3 weeks after treatment. So it essentially compares that. So for instance, this means what? So this means 3 weeks after treatment, what's the effect of having a counsel court approved arrests. Well, it's around 0. 4. So these are long differences. So 4 relative to treatment, 5 relative to treatment, 6 weeks after treatment, so on and so forth. Okay. And it looks like that there is not much effect, unlike the original results that showed us some effect, right? All right, so I mean, you can do the same to the second outcome. Okay, so it's just the same. Everything is the same. I'm just changing the outcome here. Okay, log median duration. Let's look at the log median duration. So let's go back. Look, this was negative and statistically significant. So it was showing us that having a counsel actually was decreasing median arrest duration by around 15%, right? So exponentiate that number. So it was around 15, and then subtract 1, it was around 15%. So it was a negative effect, right? So counsels were actually helping, at least not helping, but making it, but helping the suspect. I mean, that was the case. But look, oh yeah, see, look at the ATT here. It's actually, I mean, it's the sign is also reversing here. So now it's positive. Obviously, standard error is huge. So, the confidence interval, the band is also massive. But the sign even flips here. So it's not statistically significant. So again, counsel, it looks like that is not having an effect here either. So the median duration of arrest is not changing. Okay. Then you can again do the event study by length of exposure. Again, this time I'm aggregating. So look, it's just the same model. Let me go back. See, I'm just aggregating. If you just do aggregate simple, that's going to give you a single ATT. Okay. Then if you just do aggregate by calendar, it's calendar, so that's dynamic. So it's going to give you ATTs by length of exposure. Okay. And that's also null. So the conclusion is actually quite different from the conclusion in the original paper, right? Once we use Callaway and Sant'Anna. Yeah.
The more complex method to explain why we cannot replicate results of different intervention programs or education programs, right? Because I think it's similar, like for intervention programs, for example, we have different schools. Okay, we collect the data, but not every school has the education, let's say, at the same time. So it's not the reason why not replicate.
Yeah, I mean, I think one thing is, we need to also give credit to authors. I mean, this is 2017, so they were doing the best they could back in the days. I mean, this was not known back in the days, right? So, but yes, now, I mean, now we know that two-way fixed effects might be problematic if there is staggered timing, right? Because, we discovered that, oh, hey, there are all these forbidden controls in two-way fixed effects under the hood. We don't see it. Then we should do this more transparently. And all these smart people come up with all these different estimators, right? And once we, use this, results, it looks like they are not there. But obviously, this is, I mean, they were probably doing the best back in the days. And this is not very old, 2017. So, but still, I mean, this is that's, one thing. That's why I gave that repository of the ID. This is a very dynamic area. You see new papers coming out. So you need to actually read, be exposed to that, to get the most recent stuff.
You know that running intervention studies of hard. I think that's one of the
I mean, in psychology, one thing is, I think you are already doing experimental stuff most of the time. I mean, economists, political scientists, sociologists work with observational data more. That might also be the reason why psychologists aren't, because they don't have that problem. We do have that problem, right? Observational data. I mean, there needs to be observational data to use the ID, right? So, because in experimental data, it's easy. Conducting experiment is not easy, but once you have the data, it's just difference in means. if everything is working great, then just look at the difference in means and you're free to go. Here, I mean, life is not that easy with observational data. So that's why, yes, I mean, we need all these different methods. So yes, I mean, it looks like that the results didn't survive. Okay. So the main results, I would take with a grain of salt, right? So these results are probably not there. I mean, obviously it doesn't mean that councils are not working. They help people a lot, but in this specific setting, at least within this time frame, I mean, the results are not holding. Okay. Well, all right. I mean, this is all I have. Any question? By the way, this is just one of the many alternative estimators we could use. And Callaway Sant'Anna is one. There is one problem with Callaway. I mean, people say it's not very efficient, meaning that standard errors, are usually high, depending on obviously the data you have. So there are other estimators where you can have more efficient, you can gain some efficiency, but there are there are trade-offs, and I'm also not an expert on that. But check some of the references. There's one nice review that I actually had in my slides. Read that, start with that, then move to the papers, original papers, maybe. All right. Any question? Well, if not, we can go to lunch, I suppose. Yeah.
They can ask their questions to you at lunch.
Yeah, it's fine. Totally fine. Yeah, we can talk. And I think I'll attend Ali's section, so I'll be here for a while. Yeah.
Thank you, hocam.
Thanks.